about coding standards for variable expansions in Shell. In Shell, the dollar symbol or dollar sign is used to indicate that the following character or series of characters hold a value that can be accessed or utilized. This code snippet serves as an example to understand the concept of variable expansion. As you can see, we are initializing a variable named var and assigning a string value of var to it. Then, we are using echo to do what is called variable expansion, which essentially means accessing the value of a variable through a command or process so it can be used or read by it. Since the echo command works by displaying a line of text when invoked, this means that this script will display or print value of var to the terminal when executed. Let's analyze two versions of the same script, one with the presence of curly braces enclosing the name of the variable we want to expand, and the other one without. As we can see, both versions of the script produce the same exact output if we write it with and without the curly braces. So what is really the reasoning behind using them? Well, let me show you a few differences. In this script, we are attempting to expand the same variable using the dollar symbol without the curly braces on the first try, while attempting to append an additional string at the end of the variable name. This will produce an error, as the shell will be unable to expand the variable because without the curly braces, there is no delimiter as to where the name of the variable ends and where the appended string begins. By running the script, we can see how we are intending to expand the height variable, and then we want to append the centimeters abbreviation right next to the expanded value without a white space in between. On the first try, without curly braces, the result appears to be empty, as the variable height centimeters doesn't exist. Surrounding the variable name with curly braces protects the variable, so we can add the centimeter suffix at the end to get the desired result. So, most of the times, we will expand variables with curly braces. Some acceptable instances where curly braces expansion can be overlooked is for command line arguments or special shell variables, which we will learn during this course. Also, generally use double quotes to expand variables. More specifically, using double quotes to expand a variable will prevent the variable to be split into different elements. What do I mean by different elements, by the way? In Shell, there is a special environment variable named ifs that defaults to a tab, space, or line break. Any word contained in a string variable separated by tabs, spaces, or line breaks will be considered different elements when parsed by the Shell interpreter. Here, we see an example of how a variable expanded without double quotes gets split into a list of 3 elements instead of one atomic value. So, by looking at this, a list of reasons to not expand with double quotes include variable you might want to treat as lists, like the expanding datash sample shown in the screen, where we want to iterate the server 1, server 2, and server 3 literals as separate elements, versus this expanding to datash, where using double quotes to expand the variable results in the for loop treating the variable as a single element. In conclusion, for directory paths, file names, URLs, better use double quotes for expanding. When in doubt, also use double quotes. It's worth saying that the dollar symbol can also be used in combination with other characters to indicate different types of expansion or substitution. We will have a lecture for each type of expansion later in this course.
More. This time, however, we will explore those concepts from a scripting perspective. This means we will show examples on how to take advantage of those basic concepts and stack them together for good scripting practices. And by the way, knowledge acquired in the beginner shell scripting course like looping and branching constructs to perform tasks repetitively or conditionally are expected, as we will very often show code utilizing these concepts, and there isn't really a section dedicated to learning those from the ground up. We will, however, include some exercises in the labs so you can get practice with them and chop your programming skills. Before you begin the next lecture, I want to take a step back and redefine some notions and philosophies that will be utilized a lot going forward. So please be patient and stay tuned. Scripts are like executable programs that run from top to bottom, similar to imperative programming, which means giving the computer a series of commands that execute in a specific order. Some commands we type on the command line are executable programs as well. Each program or script, regardless of the context, has a standard life cycle. This is true for any program written in any programming language. When scripting in Shell, we include in our scripts other program executables, along with built-in commands, conditional statements, and special syntax to automate repetitive tasks. In this course, we will keep in mind the program standard lifecycle and apply a lot of those principles to create good, reliable scripts. Even though shell scripting is typically based on imperative programming, I want you to think of shell scripting as much more than just piling up commands on top of each other that you expect will run from top to bottom. There are cases where a script load doesn't run from top to bottom, with functions for example. Regardless if they're declared at the top of the script, unless we call them, they will not execute, like the sample we have on the screen. I also want to enforce good scripting practices so that we code in a way that we only read the last line of our script if everything else prior went well. Our scripts should accurately reflect a story of what went behind the scenes when running. Think about any task in the real world. If you team up with someone and you are supposed to take the kids to school and someone else will go and pick them up later, in the event where you only take one of the kids because the other was sick or something, reporting accurately what you did and what you didn't can save a lot of trouble. If someone assumes something was completed and it's incomplete or vice versa, the outcome can be catastrophic. In the same way, if we write a script that is supposed to create a lot of directories, but one of the directories couldn't be created for any reason, we should return an error message and stop the execution. Otherwise, another script, program, or process that runs subsequently, which is relying on our script to have created all of the expected directories successfully, will crash, creating a domino effect in the operations and potentially causing an incident. So, we will learn how to deal with unforeseen events and errors, and I will give you tips on how to create good scripts that handle events accordingly to reflect what really went through accurately. And I'm excited to begin this learning journey with you. See you in the
A
next
solid
lecture.
understanding of the flow a script follows when executing will be very beneficial for shell scripting, as it can help you be more efficient, save time debugging, among other things. Complex software is different and more difficult to analyze as it provides many points of entry depending on which component of the UI was clicked, for example, as this would execute a different functionality that changes the execution order. Gladly, shell scripts are generally very linear and easier to understand, analyze, and debug, as they provide a starting point that begins from the top of the executed script, running each command from top to bottom. However, the order of command execution in shell scripting can be changed by using control structures such as loops, conditional statements, or functions. These allow you to execute commands based on certain conditions or to execute the same command multiple times with different outcomes. A basic example of a conditional statement in real life can be going to the movies. If you have ticket to the movies, you are allowed inside the theater. Otherwise, you're not. This is called a branching of possibilities that might occur depending on the conditions. Now, to advance in your shell scripting skills, being able to create complex workflows that depend on each other to continue with the automation chain of command is very important. A closer analogy outside of programming, which illustrates a well-crafted script that considers this complex workflows, is a factory analogy. Imagine that you are running a factory that produces widgets or anything really that requires multiple steps that serve as a precondition to be met before the next step can be started. Each product must go through several stations in the factory to be completed. In the first station, for example, the widget is inspected to make sure it meets certain quality standards. If the widget passes the inspection, it moves to the next station. If it fails the inspection, it is set aside for repairs or scraped. In this scenario, the inspection station is like a control statement in programming. It determines whether or not the widget, which is like a piece of data in a program, meets a certain criteria. And based on that evaluation, it either allows the widget to move on to the next station, which is like executing a block of code, or moves it aside for repairs, which is like skipping a block of code. Okay, so we are just defining that control statements allow a program to make decisions based on certain conditions. But what I want you to get from here is that there are certain techniques that can be used specific to a coding language. And in this course, I want to teach some of those techniques for shell scripting that will help create reliable and flexible scripts that can respond to different inputs and conditions in appropriate ways. There are four main programming constructs that can alter the imperative programming flow in shell scripting. I'm talking about conditional statements, loops, sourcing code from other files mid-script, and using functions. Let's have a quick crash course refresher on these topics, starting with if statements and looping syntax in shell scripting. If any of these concepts seem too unfamiliar, head over to the Shell Scripts for Beginners course to learn the basics. Here, we have an if function that will never evaluate to true because 3 will never be greater than 4. This sample is just to illustrate that there are blocks of code that don't necessarily always run. And by the way, you might encounter different syntax styles for if statements in shell scripting when reading other people's code. In this course, we will use double square brackets over single square brackets to wrap the conditions, as double square brackets allow a wider range of condition evaluation style than the single square brackets. We will dive deeper into that topic in the built-in command section. Here, we have another conditional control structure using the case keyword. We learned the case keyword in the Shell Scripts for Beginners course, but to give a quick refresher here, this code illustrates how case keyword is evaluating a variable word that can have any value really. In the sample, we want to perform different actions if the value is matched by any of the pattern 1, pattern 2, or 3 options, meaning that if word's value contains a match for those values, it will enter the code defined between the pattern definition, executing whatever statements or commands we have in between. We have an extensive lecture dedicated to the use of case for building robust command line scripts in a future section. Another common control flow statements in programming is looping. Creating loops is a control flow statement that changes the regular execution order in a script. This type of blocks allow a program to repeat code a predefined number of times or until a certain condition is met. We have the for loop, while loop, and the until loop. As you can see on the screen, there are many different ways in looping syntaxes in Bash. To illustrate my point, we have 6 different syntaxes we'll show you that more or less achieve the same result. On the right side, we have a for loop with an incrementing counter variable. This will print iteration 1, iteration 2, and iteration 3 on the screen when executed. On the left side, we have a while loop with an incrementing counter variable. This also prints iteration 1, iteration 2, and iteration 3. The differences between these two are the techniques used to exit the loop to avoid being trapped infinitely in there. While loops generally use counter variables to have a condition evaluate to false at a given point to provide a means to end the loop. For loops generally have a predefined number of times for their execution. In this sample, we see another syntax for using the for loop. In this case, we're using the seek command, which is used to print a sequence of numbers. The command is wrapped in a command expansion subshell, which helps shell treat the output of a command as if it was a variable being read. On the left side, we have an until loop with an decrementing counter variable. These two loops produce the same exact output as the other two samples as well. In this case, the until loop runs until a condition is met, so we use a similar counter variable that will keep track of the number of times we've iterated in that loop to provide a control value to help exit out of the loop when a condition is met. Now, we have a couple more techniques used for creating loops using while. We have a while loop with a range of numbers generated using seek and read, and a while loop reading from a file called fds.txt that treats each line as an iteration element. Now, I want you to see the following pattern to make looping syntax and shell way easier. Two things present in all of these different loops are a do keyword, which appears right before the block of code that we intend to execute multiple times based on a statement, and the done keyword, which indicates that anything that comes after done is out of the looping block. For now, we will not dive deep into these concepts other than seeing the syntax presented in these examples. Just keep in mind the following rules of thumb. For is generally the better choice when we know exactly how many number of times we want to repeat the loop. While and until are the better choice when we want to loop until a condition is met, but we don't know how many number of times that could take. While is better for reading files and repeat a loop over file elements. Now, when running a shell script, we can call another script or source file written in a separated file using the source built-in command or a single dot, which is also a shell built-in. To use this technique, we type dot or source, followed by the name of the script or file to be called. This will execute the commands in the sourced file as if they were part of the original script. As you can see, on the script sample on the right, there is no variable name declared, but on the left, we are showing a command snippet that assumes a conf file is present, and this file has a variable declaration name inside. When executing conf read v1 script, what's happening is that we are sourcing the conf file in the second line of the script. On the third line, we attempt to echo the value of name. In this sample, we illustrate how this executes successfully, printing the value of name to the terminal. A more appropriate implementation of the previous example would be to use an if statement to verify if the conf file exists before sourcing it. To understand this code, let's keep in mind that shell scripting with bash allows if statements to evaluate conditions to true or false inside double square brackets. What's important from this sample is to read and analyze how we are now creating multiple branches from a basic script flow by using techniques like sourcing files and using conditional statements, but also the reasoning behind teaching this right now. As we've been talking about how scripts should only continue when pre-made conditions are met, we are pairing this idea of writing scripts in this way with the analogy of a factory producing widgets, where we only want to move to the next phase of the widget production process if the previous conditions were successfully met. In this sample, we see how in doing cat to a conf file, we get a no such file or directory, which illustrates the absence of the conf file in our current directory. On the right side, I'm illustrating a strategy to evaluate if a file is present. The syntax -f evaluates a value as true if the string's value is a file that's present. In this case, we're expanding the conf file constant as the expression to evaluate. I'm doing this because good shell scripting involves anticipating to the fact that a file might be absent when we run a script, so we want to create alternatives to keep the execution going if possible. The purpose of this script is just to echo a name. So if the file is absent, which means the square bracket condition will evaluate to false, we will initialize the name variable inside the script. Then we will expand the variable with echo to print it to the terminal as the second command illustrates. We will learn more about the use of square brackets for conditional syntax in the following lectures. This is an illustration of the more appropriate implementation of the script we saw in the previous example, which illustrates how the script would behave if the conf file is present. As you can see in the sample, the script now prints Juan Carlos to the terminal when executed, and this is because we are assuming the conf file is present this time, so we are executing the source command inside the if statement. We will see functions as another way to control the imperative style flow in our shell scripts in the upcoming lectures, but first, we will revisit some topics to make sense of some of the concepts we will explore when learning functions. I want to encourage the use of functions as much as possible when doing shell scripting. In the previous lectures, we went over how scripts written in Bash follow an imperative programming style for the most part, and how the commands written from top to bottom generally execute in that order. We also went over 4 main scenarios when scripts don't execute from top to bottom. These techniques can be used to control the flow of our scripts. I'm talking about conditional statements, loops, calling or sourcing code from another file, and functions. In this lecture, I want to talk about functions and why they're an important topic to master, mainly because functions encapsulate blocks of code that can be called repetitively without having to rewrite them repeatedly. To think about how functions work with a real-world analogy, imagine that you're a chef at a restaurant and you're responsible for preparing several dishes, such as salads, sandwiches, and pizzas. Each of these dishes has a specific set of steps that must be followed in order for them to be prepared correctly. Following this analogy, the first time you prepare a dish, it's okay to take extra attention to detail, as you're meticulously designing the most efficient steps to prepare the dish. In the long run, however, carefully following the same steps over and over can become really time-consuming and error-prone. If a chef could capture the steps that were carefully followed for a dish and abstract them into an implementation, that would allow those steps to be reused in the same order each time, with all the ingredient considerations, measurements, etc. This would make your life at work a lot easier, and gladly, when coding scripts, the use of functions can help you reuse a series of steps we've carefully put together by thinking about all possible scenarios. We just need to encapsulate those steps into a function bracket and call them each time. This way, you wouldn't need to remember or look up all of the steps every time, and moreover, you wouldn't have a chance of making a mistake, because the function is already hard-coded and it's just like pushing the replay button every time. A good function is written when you can also input values to make a generic set of steps more concrete to a given scenario without breaking the existing functionality. In the chef analogy, this would be like having the ability to run a function to make a dish while excluding certain ingredients. This would be similar to performing certain actions like creating a backup, for example, where we want to pass as an argument which file to perform the backup against. This sample code illustrates my point exactly. Writing scripts that handles backup files is probably one of the most common tasks we do as DevOps. However, thinking about all the scenarios that we want to consider is generally just a one-fit solution that works for a specific use case. Here, we are creating a backup directory, and then we are copying a file named file.txt into it. Then we use a tar command to compress the file into a file named backup.tar.gz, and then we exit our script. Without taking much into this implementation, imagine that you find the perfect order to pile up your commands to help you create the backups for your specific directory structure and your unique situation. But then, every time you need to make a backup, you have to write those sequential steps in the same order over and over across your script. You'll end up having a hard time maintaining your code this way. A better approach is to use functions, as they allow to group together a set of instructions that can be executed repeatedly. So once you have perfected the steps that help you resolve a particular task, you can group them together in a function. This way you can just call them each time they're required, as they can be reused while your script grows larger and more complex. Functions make your code more organized, efficient, and easier to understand. Let's use the previous example of cloning a Git project with command line arguments and improve it further to include the use of functions. We could go from here to here. In the second example, we can see how the script begins by setting a variable get_URL to the value of the first command line argument. This argument should be the URL of a Git repository that you want to clone. The script then defines 2 functions, getClone and findFiles. The getClone function takes a single argument, which should be the URL of a Git repository. The function will use this argument on the getClone command to clone the repository. The findFiles function uses the find and wc commands to count the number of files in the current directory. Finally, the script calls the getClone function with get_URL as its argument, which will clone the Git repository specified by get_URL. The script then calls the findFiles function, which will count the number of files in the current directory. Alright, so now that we've talked about benefits of using functions and we've seen samples of how functions can be implemented to improve our scripts, let's talk about function declaration syntax. In Bash, there are 2 main ways in which we can declare a function. The most common way, and the way you'll see it being used in this course, is in the way it is defined on the left-hand side. Another way to declare a function is by using the reserved word function. As you can see, the example on the right lacks parentheses on the function declaration block. However, the parentheses can still be used along with this syntax, but they're just optional. These two function declaration syntax can be used with one-liners as well. This means just typing them directly in your terminal, and you should be able to see an output similar to the one shown in the screen. As you can see, invoking a function from the command line requires just typing the function name after it's being declared. These two samples produce the same output, but as defined earlier, we will generally prefer the function syntax declaration with parentheses and avoid using the function keyword. This is for style and portability with previous versions of Shell. Let's now talk about declaring local variables inside a function. Most coding languages follow similar principles of variable scope. The local keyword is used to declare a local variable. When a variable is declared as local, its scope is limited to the function. This means that the variable cannot be accessed or modified outside of the function or script where it was declared. Variable scope is a foundational concept studying programming and software development. But understanding that local is a modifier that prevents a variable's value from being accessed from outside of a function where it was declared sufficient for shell scripting purposes. As you can see in this example, trying to echo the value of var1, which is declared as local inside the function, produces an empty output, as the scope of the variable is limited to the function. Here's a corrected version of this script where echo var1 is called from inside the function. In this version, we get a hello output as we are making a correct use of the variable scope by attempting to access it from the correct place inside the function. There are several advantages to using functions in programming: to organize and reuse code, to make code easier to read and understand, and to divide a large program into smaller, more manageable parts.